Let's do a helix example. Let's let f and g be cosine and sine, and let h of t, a third coordinate, be just t. Let r of t be a three-dimensional vector, f, g, and h. All this stuff can be the same as before. The velocity vector is still the derivative of the position vector. The acceleration vector is still the derivative of the velocity vector. The speed is still the magnitude of the velocity vector, though I do need to, if I do the formula this way, I need a plus h prime of t squared. Unit tangent vector is still the normalized velocity vector. Take the velocity vector and divide by its length, which is the speed. The unit normal vector is the normalized derivative of capital T. Tangential component of velocity is still this, the derivative of the speed. Normal component of velocity is still this. And we can still figure out the curvature. We didn't have time to actually do that with Mathematica last time. Let's see if we can quickly do it now. Which formula should I use? These two were for two-dimensional situations. This for a function, y equals f of x. This for a parametric curve in the plane. Got to use one of those formulas. If you're doing it by hand, which of those is easiest? I think these last two are typically easiest. Let's check that they give the same thing. First one involves, it's the magnitude of the cross product of the velocity and acceleration vectors divided by the magnitude of the velocity vector cubed. Okay, let's go ahead and use that first here. Magnitudes of vectors can be done as square roots. Cross product of velocity and acceleration can be done like that, with cross. But I'm taking its magnitude, so I need to dot it with itself. Then I'm dividing by the magnitude of the velocity vector cubed. I've already got the magnitude of the velocity vector in there as the speed. So I could just do speed of t cubed here. Yeah, in general, it's a complicated thing, though this does simplify quite a bit, actually, to a constant. Will simplify show that? 1/2. What is this graph? I already said it. It's a helix. Spiral. Spirals like this, helices, have constant curvature. It was a crazy formula, but it simplifies to a constant. You can do this by hand because cos squared plus sine squared equals 1. 1 there, 1 squared there, 1 to the 3/2 there, or 2 to the 3/2 there, excuse me. Do you have any homework about this? You should be able to figure out the radius of the osculating circle. What's the radius of the osculating circle? If the curvature is 1/2, something you should have read about is the radius of the osculating circle is 1 over the curvature. 1 over 1/2 is 2. If you try to draw the osculating circles in these pictures, at any given point, it would have a radius of 2. And it would be at any given point, it would be the plane, the osculating circle would be in the plane of both t and n. And it would be sort of the plane that the curve is most close to being in at that point.